Then I'll just start. Can everyone hear me? All right. Hi everyone. Thank you all for being here. I'm Slik. I'm a computer vision scientist at TNO, which is the Netherlands Organization for Applied Scientific Research. And I'm going to tell you something about how we detected building elements and then used them in prediction for renovation solutions on an address level. So let me explain the problem we're facing first. We have about 1.5 million addresses in the Netherlands that need to be renovated because they still have very poor energy labels, and we need to scale up that productivity, obviously. But the problem is that a lot of the renovation solutions that are being applied, it happens on a project basis. So each address, obviously, they make a whole plan and they execute the plan. So industry needs to move to a more product-based approach where you develop products that that can be applied universally or at multi addresses. And some companies already have some retrofitting solutions that are multi-applicable, and so at TNO, we've developed a method, a machine learning method, together with open data to predict the applicability of those retrofitting solutions to certain addresses. But what we have found is that the open data, it still kind of lacks the information depth to accurately describe the individual addresses. So then computer vision comes in. A lot of the features of interest that we were interested in, we found that they can be detected from street view images, but to collect these features, we would need advanced computer vision models. And yeah, so the problem with the computer vision models, though, is that the data that we are looking for is very domain specific, so it's expensive to get the training data. Or yeah, it's not available yet. Sometimes it is. But what we want is we want to have a robust method that we can use where we only have a few examples of what we're looking for, and then we can detect this in Google Street View. So I want to explain where the research idea came from, or the computer vision approach idea came from. We drew inspiration from vision transformer research. So these are vision models that are quite similar to the BERT transformers in NLP. They, instead of encoding text, they encode images in a meaningful way. These vision transformers, they produce global and local representations of an image. So the embedding the vector that represents an entire image, but also locally. Here I kind of want to show, it's maybe a little bit difficult to see actually in the image, but in this image, a vision transformer was used to find similar areas with a query image. And for example, in the cyclist, there's a little square around in the face of the cyclist, and you can see in the other images that they were looking for the most similar area in that image, and in most of those images, or in all of them I think, an area in the face is also detected as the most similar area in that image. So basically, if you have a local representation in one image, you can use that to find similar areas in other images. And we apply this to building elements and try to find building elements in a similar way. So in this slide, I have a schematic drawing of what that looks like. So our annotation process looks slightly different because we want to sample the areas of the image that we're interested in, and also explicitly tell or annotate what areas we are not interested in. So in this annotation, we have a green box around the dormer, which is one of the building elements we were interested in. And then we have red bounding boxes, which define basically negative areas. Then this is kind of like a rough representation of what the vision transformer looks like. The vision transformer transforms the image into patches. of 14 by 14 pixels, and then processes it and produces a vector for each of those patches. And while we do that with the annotation, we can keep track of which of the patches are of the building element and which are not. Then we do this for multiple images, and we collect all the vectors, and then we fit a machine learning classifier in the embedding space to distinguish between those positive and negative embeddings. So the experimental setup, this is kind of like what we have essentially done. We've done it for 7 different building elements. We have the solar panel, the dormer, the balcony, chimney, roof, window, roof ventilation, removable panels. And for each of these building elements, we have annotated only 21 images, which is obviously not a lot of effort. But we also have 100 test images. These 100 test images are not annotated with bounding boxes, but just on an image level have a label of whether this image contains that building element or not. That's also just to make the annotation process as fast as possible, basically. And we tested it with 2 different vision transformer and 4 different machine learning classifiers, and just kind of like set up a study. Here is one of the plots from the paper, which shows on the horizontal axis the number of training images and how the trend kind of shows that with more example images, the balanced accuracy kind of goes up, with the best combination of the models being the Dino V2 with a random forest classifier. At 21 images, it gave a 95.8% accuracy across all the 7 building elements in the total of 700 test images. And this is kind of a visual representation of what that looks like. It's always good to inspect what the model does. It gives a bit of explainability, and it shows that it's actually detecting the areas that we want to detect. So we see the red highlighted patches on the building elements that we wanted to detect. In the bottom right, it's quite difficult to see, but it's a small ventilation on the roof that was detected there. So then what happens when we detect these building elements from Google Street View on our data sets that we have created with industry partners? So we have 5 different data sets about different renovation solutions, and we compare what happens when we use our open data features with when we collect a Google Street View image for each of the address and then detect the building elements on it. All right. And this is the performance. The performance was kind of like expected. Most of the building elements we detected, they were situated around the roof. And we have a data set that predicts the roof insulation renovation solution for single family buildings. And there was an improvement of 4.8%. So that's in line with using image features is useful. And the removable panels for single family buildings is one of the features that we actually predicted directly. So there an improvement is expected. For the other ones, it is also kind of like they're unrelated to the building features. The floor insulation is not related to any of the features we predicted. So then what does this mean for the future? Most difficult cases to detect for us were kind of like really small elements like the roof ventilation, or elements that are visually variable. So we might need a bit of higher resolution or multi-scale inferencing. Another issue we had is that Google Street View, the standard query, just you see multiple addresses at the same time in one image. So we need to actually zoom in better on each address and use geographic information systems together with Street View, which we're working on now as well. And yeah, some of the data sets that we were using were actually quite small for the retrofits, so we need to expand them and further validate them. That was it. Thank you all for listening. I'm happy to take any questions.